Okay, so we are going to look at how gravitational potential energy changes when we start looking at these larger size objects. So here we are looking at gravitational potential energy. When we looked at it the first time, when we were near the Earth's surface, what we said was that potential energy was mgh, where g was that free fall acceleration. Now, you may remember that when we were dealing with forces, that forces are the negative derivative of potential energy with respect to position. So if we think about that with our universal gravitational force, where it was G m over r squared, what we got from this tells us that our universal gravitational potential energy is negative Gmm over r, where r is the separation distance. Now, things here get a little weird because before, when we were looking close to the Earth, as we got really just right on top of the Earth, our potential energy was to 0. Well, for universal gravitational potential energy, we get to 0 when our r is massive, when our separation is huge. So that tells me that if we look at the limit as r goes to infinity, as r gets really, really big, this gets big, which tells me the entire thing is going to 0. So our potential energy is decreasing as the particles get closer, but now our potential energy is negative. Our potential energy is negative, so it's still decreasing, but we got to watch out because it's negative. So our potential energy is the energy that's associated with a system of particles. So if that system contains more than just 2, we have to play round robin when we calculate the gravitational potential energy. So here we have a situation where there are 3 particles. Particle 1, particle 2, and particle 3. If I want to find the gravitational potential energy, I have to consider the gravitational potential energy between 1 and 2, the gravitational potential energy between 1 and 3, and I cannot leave 2 and 3 out. I have to cover each set. So each pair has to be covered. So we have to be very careful and make sure that we cover all of those. So I did kind of give you a hint here on number 6. So if we are looking at the derivative of u with respect to position, so the negative derivative of u with respect to the position, in this case our position is r, so we're looking at negative d dr of our potential energy equation, which is going to be negative g m over r. So our negatives are going to cancel. So we're going to get g m, those are going to stay the same. And what we're really going to have is a derivative with respect to r of 1 over r, or r to the negative 1 power. So we're going to kick our power out. We're going to get g m over our new power is to the negative 2 because we subtract 1, so that's where we get over r squared. That's our force. And it's negative because it is attractive. It is pulling into the center. So that's what we're getting. We're getting those connections between potential energy and force are connected using calculus. So let's look at an example here. If we want to fire a projectile upward, now in in theory, there is a way that we could fire it with a speed that allows it to move upward for forever. And it would only come to rest when it's way out at infinity and beyond. So we call that minimum initial speed that we need the escape speed, because we have to get outside of the Earth's atmosphere. So when the projectile is infinitely far away, all the kinetic energy has been converted to gravitational potential energy, which by definition is zero. So that means when we get infinitely far away, the entire thing is at rest. Gravitational potential energy by definition is zero, and I know this seems a little weird. Now, remember, as it gets closer, our potential is negative. Okay, so what is this big R? That is the radius of the Earth. So that is the Earth's radius. If we are trying to escape the Earth, if we are trying to escape Mars, that would be the mass of Mars and the radius of Mars. But we're just dealing with the Earth. So we're going to get all of that as zero. So kinetic energy is 1/2 mv squared. Universal potential energy is going to be negative g, mass of the Earth, mass of whatever it is we're launching, over the radius of the Earth, and that's going to equal zero. So that means the mass of the capsule, in theory, does not matter. In theory, I can divide by that mass. So that's going to give me that 1/2 velocity squared is going to equal, when I move this over, g, mass of the Earth, or mass of the planet, over the radius of the Earth squared, or not squared, just radius. I'm going to move that 2 over, so I'm going to get the square of the escape velocity, our minimum velocity. It's going to be 2g, mass of the Earth, over the radius of the Earth. So that is where we get, this is the absolute minimum speed that we would need to launch at to escape the gravitational pull of the Earth. That's just how much we need just to get away from the Earth. That's not physically getting outside, dealing with wind resistance, any of that. This is ideal situation, just getting away from the gravitational pull. So, as we're talking about that gravitational pull, let's bring Kepler back into play. So Kepler had those 3 laws, and we've talked about them before. We're going to talk about them again. So his first law states that all planets move in an elliptical orbit. The sun is at one focus. So this is Kepler's first law. Now, the fancy name for it is called the law of the orbits. Everything is an elliptical orbit. Everything. The sun is at one of the foci when we're dealing with these planets. So, the second law is what we refer to as the law of areas. Now, what we've kind of done in the past is we've glossed over these a little bit. And we've said, okay, well, if I attach a line here from the orbit to the sun, and I let time elapse, it's going to sweep out equal areas in equal time. So what does that mean? That means here it's going to move fast. Here, my omega is going to be slow. Now, why do I say my velocity is going to be faster over here? Quite frankly, because I've got a shorter arm length. So I've got to sweep out equal area. I've got to go faster here to get the more area that I would have with just because of the length to make up for this long triangle-ish shape. So that is what we refer to as the law of areas. Now, Kepler's third law is what we refer to as the law of periods. Now, we've kind of glossed over this in the past and not given the full equation. What we typically say is something like the square of the period is proportional to the cube of the semi-major axis. Okay, well, what does that mean? Well, remember how we said that we have an elliptical path and the sun is at one of the foci? Okay, if I chopped this into quarters, this is the semi-major focus, semi-major axis. This is the semi-minor axis, so we're dealing with just half of the long side. So half of the length of the ellipse. That's the semi-major axis. So that is what we were looking at here. That t squared is proportional to a cubed. Now, what is the constant that goes in between? It's going to be 4 pi squared over gm. Now, we could create that formula, and that's what the steps here are showing. Because we said, okay, well, force is equal to mass times acceleration. We can plug in the gravitational force. Those masses are going to cancel. Acceleration is centripetal, so it's going to be omega squared r. Move everything over, and we would get that gm is proportional to all of this, and we could calculate omega by using, basically assuming it's close to a circle. We could go, okay, well, that's 2 pi over the period, and then go from there. There is a way that we can actually derive this equation. We do not have to. So we do need to know that the period squared is proportional to the semi-major axis cubed if we are dealing with an elliptical orbit. So how are we going to get kinetic energy? Well, if we think about a satellite's orbit being kind of in an elliptical path, we've said that for a circular orbit, our potential energy is negative gmm over r. Now, we're going to have to use Newton's second law to get the kinetic energy. So what do we know? Well, we know that force here, so force is equal to mass times acceleration. That's our net force. Well, that's going to be Newton's law of universal gravitation. And we're going in a circular orbit, so it's going to be mass times v squared over r. Those masses are going to cancel. One of the r's is going to cancel, so we're going to assume that our radius is bigger than 0. Good math skills here. So, may have canceled that mass a little early here. So, what do we know? Well, kinetic energy is 1/2 mv squared. Well, I have an equation for v squared. That's gm over r. So this is going to be 1/2 m gm over r. So what I get is that this is going to be 1/2 gm m over r, which tells me that it is half, the magnitude is half of my potential energy, but it's positive because it's kinetic energy, and so we're going to have that negative in front. So what we get is that the total mechanical energy, for an orbit is right here. And yes, it is indeed negative. It is negative. If we're dealing with an elliptical orbit, we're just going to replace r with a, and we get the elliptical total mechanical energy. So, when we get back in the classroom, we are going to start looking at some examples for this, and we're going to talk about eccentricity. I'm going to challenge you to go ahead and read up on this gravitation, and be prepared with questions.